Let's solve some questions from the 2004 British Physics Olympiad Senior Physics Challenge. The first thing that we need to look at is the problem-solving format. So there will be some multiple choice questions which are going to be followed by some longer answer questions. Okay, question number one, exciting. Newton's law of universal gravitation describes the gravitational force. Force is proportional to the product of the two masses and the square of the distance between them. There is this famous constant of proportionality. In fact, Newton's law can be written as the magnitude of that force is equal to gmm, where lowercase m and highercase m are two masses, divided by the distance between them, let's say r squared. The best way to tackle problems like these is to simply rearrange for g, and g will be equal to fr squared, divide that by m and then m. Now I like to simplify and say that force is equal to mass times acceleration, r squared over m. And notice how those two m's are just going to cancel out. So what units are we going to be left with? Tell you what, let's write this over here. We're going to have the units of acceleration, which are meters per second squared, multiplied by meters squared, which is the units for r squared. Divide that by kilograms. So this here is going to give me meters times meters squared is going to be meters cubed, s to a power of -2, kg to a power of -1. Now this here corresponds to the correct answer being C. Let's have a cup of coffee before we proceed to the next question. Ouch, that's a little bit too hot. Okay, so the distance from the Earth to the Moon is roughly 1 light second. Approximately how long would it take to you to walk this distance? Well, I do like walking, but the answer is probably quite a long time. So, okay, 1 light second. So 1 light second, that's just the distance traveled by light in 1 second. So the speed of light is 3.0 times 10 to the power of 8 meters per second. So that means that the light second is, let's say 1 ls is just 3.0 times 10 to the power of 8 meters. This is an approximation question, so the clue is approximately, that's written in the question, so we can assume that on average we travel about a meter ruler a second, maybe a couple of meter rulers, but let's just for the ease of math choose 1 meter per second, and then we can just use the fact that the time is going to be the distance divided by the speed, which is going to be 3.0 times 10 to the power of 8 divided by the speed, which is just 1 meter per second. Now all we need to do is convert that time, 3 times 10 to the power of 8 seconds, into years, because our answers are actually in years. Okay, so 3.0 times 10 to the power of 8, let's divide that by 3,600 for hours times 24 times, let's say 365 days in a year. Okay, I get to use my brand new calculator, and I'm really slow when I start using new calculators. Do you find the same? Let me know in the comments. There's no single button for changing my answer to a decimal. Okay, so this here is giving me around 9.5 years, which is pretty close to 10 years, so correct answer is going to be B. Notice that in approximation questions that all the other answers are factors of 10 away. So if we had taken the average speed to be twice that amount, 2 meters per second, or even half that amount, we still would have had a roughly similar answer within a factor of 10. On to question number 3. So a metric predecessor to the SI system of units is the CGS system, which is based on centimeters, grams and seconds rather than meters, kg and seconds. And then we're given that 1 dyne is the unit of force in that system. It is defined as the force which accelerates a mass of 1 gram at 1 centimeter per second squared. Okay. So to work out how many newtons is the equivalent of 50 dynes, let's just consider 1 newton, and I'm just going to write this up here. So we know that 1 Newton is equal to mass times acceleration. So it's going to be 1 kilogram per 1 meter per second squared. So if we were to change the kilograms to grams, we are going to get that 1 Newton is actually going to be equal to 10 to the power 3, and then meters to centimeters, that's going to give us 10 to the power of 2 s to the power of minus 2. And what we have over here on the right hand side is that old unit, the dyne. So 1 Newton should be 10 to the power of 5 dynes, or dyne, which of course means that 1 dyne, on the other hand, just dividing by 10 to the power of 5 is going to be 10 to the power of minus 5 newtons. So if I had 50 of those, let's multiply that by 50, we're going to get 50 times 10 to the power of minus 5, which is 5 times 10 to the power of minus 4. Correct answer has got to be D. Now the coffee is cool enough so I can actually enjoy it. Question number 4. An eccentric billionaire wraps a rope around the Earth's equator. She then wishes to raise the rope above the ground by 1 meter along its entire length. Approximately how much rope does she need to insert into the original rope? Ah, those billionaires, hey! So the circumference should be equal to 2 pi r, and then we're looking for the amount of extra rope. So if we add 1 meter along its entire length, let's say that the new circumference is going to be r plus 1. Okay, and then from that we need to take away the just 2 pi r, where r in this case is just the radius of the Earth. Well, this here is just going to give me 2 pi r plus 2 pi, take away 2 pi r, and look at that, we don't even need a calculator. The answer is about 2 pi, which is going to be around 6.28 meters, around 6 meters. Correct answer has got to be B. This one here I really like, and it really made me think the first time I came across this question. So here's what I think is the best way to actually tackle it. Okay. We've got a child on one of these, which is a sled, sledge, or sleigh, is illustrated in the figure below. Slides down a smooth, snowy hill onto a flat surface. So immediately the first sentence is actually telling me that there is no friction during that. Because it says smooth, this is typically a physics kind of hint telling us ignore friction. I don't think this is particularly physical. In fact, the very first time I started this question, I ended up writing a load of maths trying to think about how the friction will vary along the slope. Really interesting, but not what the question was after. So they descend down the hill, and then they actually hit a flat surface eventually. So this is where there is some friction. The next time she does this, her brother joins her on the toboggan, doubling the mass descending the slope. On the flat surface, the frictional force is proportional to the weight, but that's only on the flat surface. Okay, proportional to, let's say, W. How far do they slide across the horizontal surface this time? Now, this problem boils down to 2 things. Number 1, the speed at which they reach the flat surface is independent of the mass. Why is that? Well, in general, if I was to drop 2 things in a vacuum, and in this case, we're ignoring all resistive forces, totally not physical, but we need to assume that the only acceleration is just equal to g sine theta, which is going to be the acceleration along the slope. It's independent of the mass. So they reach here with the same speed, let's say v, regardless of the actual mass. How far do they slide along the horizontal surface is determined by the work done by the resistive forces. Let's even write this down. So they reach the bottom of the slope with the same speed regardless of mass. The trick though is that even though they reach with the same speed, if the mass is doubled, the energy in the system has also doubled. So if the mass is doubled, the kinetic energy, which is just a half mv squared, has also doubled. How far they reach is determined largely by resistive forces, so the change of energy is going to be equal to the frictional force, let's just say F, multiplied by the distance traveled. This is because change of energy is equal to work done, which is equal to force times distance. Okay, so the distance is then going to be equal to the energy divided by the force. If I was to double the mass, then I'm going to get a factor of 2 up here, but then also a factor of 2 for the frictional force. Why has the friction doubled? Well, on the flat surface, the friction is proportional to the weight. Well, that leaves us to the distance being completely unchanged. So if originally the distance was d, then if you double the mass, you have double the kinetic energy, but also double the friction, meaning that those two factors will cancel out. Correct answer has got to be B. Question number 6 is about one of my favorite things ever, and that is Einstein's theory of relativity. And it's about the gamma factor in particular. We need to sketch this famous piece of mathematics that describes how there's a cosmic limit to the speed that we can reach in the universe. I have a really long video on Einstein's theory of relativity. I'll link that in the description if you want to learn beyond this question. But how do we decide what this thing looks like? Well, it's really important to look at limiting behavior. So we know that if the speed starts approaching the speed of light c, the equation probably breaks down. Well, we can actually see that because if that's the case, we're just going to get 1, the square root of 1 minus v squared, which is going to turn into c squared minus 1. And then look at that. We are actually going to get 1 over the square root of 0, which is just 0. And that's not good. This is completely undefined. So we need to get an asymptote around the value of the speed of light. So because of that, well, this one here, it can't be that, and this here is not exactly a very clear asymptote, so we can probably get rid of this. We can also see that it absolutely cannot be this one, because if the speed is greater than the speed of light, we are going to get 1 minus a larger number, which is going to be the square root of a negative number, which means that the result is going to be imaginary. And I doubt this question is talking about particles called tachyons. But yeah, it can't be this one. It can definitely only be A. The other way of looking at limiting behavior is what happens at really, really small speeds when v squared over c squared is negligible. Well, then gamma should be approximately equal to 1 over 1. And we can see that this thing over here has approximately the value of 1. And then as we start approaching the speed of light, relativistic effects really start becoming visible. Okay, question 7. A closed cylindrical jar is half full of dry sand. The sand grains have the same density but of different sizes, ranging from 0.1 to 1 millimeter in diameter. You shake the jar for a long time. Which of the following happens? Shall we test that? Okay, take 2. Here is my transparent panda cup. Hopefully you can see this. So what I've put in here is a whole bunch of porridge oats, and there are some larger cereal particles in there. So if I was to start shaking this, over time, hopefully you can see that the actual cereal particles should start emerging near the top. So after shaking this for quite some time, you can actually see that some of the cereal particles have already started to emerge near the top. So hopefully you've managed to see that the smaller particles essentially have the space to go through the particles, and eventually over time it's the larger particles that tend to go near the surface. I have a feeling it was called the Brazil nut effect, but yeah, do research that. So the correct answer has got to be A. Okay, two walls face each other and are initially 12 meters apart. They're steadily brought together, each traveling at 0.3 meters per second. A fly strap between the walls flies to and from each wall, moving at right angles to the planes at a speed of 1.6 meters per second. How far does the fly travel before the fly is squashed? Okay, so I actually first came across this problem when I was a physics student. There was multiple different variations to it. I specifically remember solving in class the one about this problem, but it was two trains that were traveling towards one another, and there was a bird that was flying between them. And the trick is always that you can assume the fly to be traveling at constant speed. So the first thing that you want to work out is how much time does it take for the two walls to actually meet. Okay, well, they're 12 meters apart and they're traveling together at 0.3 meters per second. So it's going to take, let's say that the time for them to travel half the distance in order to meet is going to be 6. Divide that by 0.3, which is going to be 20 seconds. So during that time, we are assuming that the fly is traveling at constant velocity. I know it's not physical because the fly is going to have to decelerate and turn around potentially, or turn in a circle and so on and so forth. But assuming that it travels at a constant velocity, we can literally just use the fact that distance is speed multiplied by time. So what is that going to be? Speed is 1.6, multiply this by 20, 32 meters. Question number 9. A cannon fires a shot directly upwards. The cannonball reaches its highest point and then returns to the ground. Taking into account air resistance, which of the following is true? Okay, so this one also took me a while to realize what's actually happening, but it's a really, really good problem. So let's imagine the actual force diagrams. Imagine that you have a projectile which has been, let's say, shot from the cannon and it's going upwards. There's going to be several forces which act on it. When the direction of motion, which I'm going to draw with blue, is upwards, there's going to be two forces acting. One is going to be the weight, and then there's also going to be a frictional force that is acting downwards. Now, when the projectile has reached its maximum point, I'm going to draw it over here, and then it's coming down, then the weight is going to be acting downwards, but now the frictional force is going to be opposing the weight, right? So the frictional force is acting always opposite to the direction of motion, which is here. If the frictional force was also acting in that direction, the times would be the same, but it's not. It's acting opposite to the direction of motion. So because the friction and the weight are both working together to slow the object down until it reaches its highest point, it's going to reach its highest point faster because it will take less time. So the time going up is less than the time coming down. Okay, question number 10. These can always be a little bit confusing. The spectral intensity of a star is the amount of energy per second falling normally on a unit area at a distance d from the star. It's related to the power by the classic equation. Okay, a student moves her face towards a 60-watt desk lamp until at a distance of 0.2 meters, she feels the heat equivalent of a warm summer's day. What is a reasonable estimate of the power of the sun? Well, that question kind of escalated pretty quickly, but I'm sure that we can calculate this. So the intensity will be similar to that of the sun on a warm summer's day with several different assumptions, but my guess is that we can probably go that the power of the sun over 4 pi, the distance from the sun to the earth squared, will be approximately equal to the power of the lamp over 4 pi over that sort of small distance of 0.2 meters. I'm just going to call that d squared. Okay, so the power of the sun will just be equal to the power of the lamp times the distance to the sun squared divided by d squared. Okay, power of the lamp is 60 watts multiplied by the distance to the sun. Let's be careful with the units here. So it's going to be 150 million, which is times 10 to the power of 6. Multiply that by kilometers, which is 10 to the power of 3, and all of it is squared. Divide that by 0.2 squared. I'm slowly getting faster in using this calculator. Squared over 0.2 squared. So we get around 3.37 times 10 to the power 25 watts, about 10 to the power 25 watts. Okay, on to the longer styled question. So let's see what we've got here. It is estimated that the average electric charge transported in a lightning strike is 20 coulombs. The energy converter is 2.4 times 10 to the power of 10. What is the potential difference between the cloud and the ground at the moment of the lightning strike? Okay, so we're given energy and we're given charge, so we know that voltage or potential difference is just equal to W over Q is the energy per unit charge. So what is that going to give me? 2.4 times 10 to the power of 10, divide that by 20. So divided by 2 is going to be 1.2, and then 10 to the power of 9 volts if my mental maths is okay. Next one, the air breaks down and becomes conductive when the voltage across it exceeds 10 to the power of 4 volts per centimeter. What will be the maximum height of the charged thundercloud above the ground so that a lightning strike can take place? Okay, so we've got 1.2 times 10 to the power of 9 volts. And then we know that we also need 1 times 10 to the power of 4 volts per centimeter. So how many of those would we need to reach 1.2 times 10 to the power of 9 volts? Well, let's just divide the two numbers. So we can go 1.2 times 10 to the power of 9, divide that by 10 to the power of 4. And this here is going to give me 1.2 times 10 to the power of 5 centimeters. So we need to convert that to meters, I imagine, because that's not very useful. Divide that by 10 to the power of 2. This here is going to give me 1.2 times 10 to the power of 3 meters, which is about, why am I writing these? It's exactly equal to 1.2 kilometers. Okay, B, in a typical thunderstorm, lightning flashes the ground at intervals of 2 minutes over the whole of the surface of the earth. The total current carried in this way between the atmosphere and the ground averages 1,200 amps. Calculate the average number of thunderstorms taking place at any instant over the entire Earth. Okay, how interesting. So let's see what we are actually given in the question. We know that the average electric charge transported in lightning strike is 20 coulombs. And okay, there's a lightning strike at an interval of 2 minutes. So we can probably use Q is equal to I times T and work out the entire charge that strikes the Earth over 2 minutes. So this here is going to be 1,200 multiplied by 120. So this here is just going to give me 144,000 coulombs that have been transferred over 2 minutes. So let's divide this by 20, and then what we should get is the average number of lightning strikes. So 144,000 divided by 20, what is that going to give me? 7,200 lightning strikes. Okay, so I think that's as far as we can go because we don't really know the number of lightning strikes per thunderstorm. So the answer should be 7,200, assuming that there is one lightning strike at a given time per thunderstorm every 2 minutes. Now, anyone who's sort of been in a thunderstorm can probably see that this is not 100% accurate, and sometimes in the space of 2 minutes you might get multiple lightning strikes. But yeah, this is what the question presumes. Case C, in order to determine whether those lightning strikes contribute much to the warming of the atmosphere, calculate the average heating power in a cubic meter of air due to those strikes if they all occur in the lowest 1 kilometer of the atmosphere. Assume the Earth is a sphere of a certain radius. So we want to calculate the average heating power in a cubic meter of air. So the power divided by the volume is what we're looking for, average heating power in a cubic meter of air. Let's start off with the volume. This here is going to be the volume of a shell, which is going to be the bigger volume, which is going to be 4/3 pi R2 cubed, which is going to be 6371 kilometers times 10 to the power of 3 cubed. Takeaway, I'm going to write this over here, 4/3 pi 6370 times 10 to the power of 3, all of it cubed. And this here is the volume of the shell, which is around 5.09, let's call it 5.1 times 10 to the power of 17 cubic meters. Now, the total power, the average power over that time, okay, so shall we just use I times V, which should work, where this here is voltage, by the way, and this here is volume. Tell you what, I'm just going to write volume so we don't get confused with the two V's. Okay, I times V is going to be 1200. In part 1 we calculated the voltage to be 1.2 times 10 to the power of 9. Divide that by 5.1 times by 10 to the power of 17. Let's see what that gives us. So I get around 2.8 times by 10 to the power of -6 watts per cubic meter. This doesn't seem like much. Is this what the question is actually asking us about? In order to determine whether these lightning strikes contribute much to the warming of the atmosphere, calculate the average heating power. So we've done this. Well, 2.8 times 10 to the power of -6 doesn't seem like very much to me, but we've calculated it. Next one, which is about a tire. I do like rotational mechanics. So, car tires, such as in figure 9, come in a variety of sizes. One particular car uses tires with a total external diameter, including the tread, of 6 to 1.5 millimeters. When new, the tires have a tread depth of 8.5. Okay, when the tires were installed, the car's speedometer was calibrated to measure the correct speed by counting the rate of rotation of the wheel. Some time later, the tires are old and the tread has worn down to 1.6 millimeters. Explain whether the reading of the voltmeter will now measure a too high or too low speed compared to the correct value. So the speed actually will appear faster than the correct speed, and this is because the circumference is now going to be smaller, so the wheel is going to be essentially rotating faster. Now, the next question I thought was quite difficult when I came across it. It is asking us, when the speedometer now reads 70 miles an hour, how fast is the car actually traveling? So the tread has worn down and the radius is now actually smaller. The thing to realize in those problems is that the car is still going to be moving at some value of its linear speed. So let's say that the car travels at a speed of 20 meters per second, just to keep it really, really simple. So if we have a car which is traveling at, it's my drawing of a car, not very good, at 20 meters per second, in 1 second it will cover 20 meters, right? I think that is actually quite fast. We should probably be traveling slower. Assuming there is a no slip condition, then 20 meters is going to be n times the circumference of the wheel. So 20 has got to be the number of rotations multiplied by 2 pi r, or we can even just say pi times the diameter. So pi times the, let's say, d1. And those number of rotations is what I imagine the sensor picks up to actually determine the speed. So I'm going to say that 20 is going to be equal to n1 times pi times d1. But also, if it's traveling at 20 meters per second, it will also be equal to n2 times pi times d2, where d2 is the worn diameter. And now we can essentially set those two equations equal to one another to determine a relationship between n1 and n2. So we can say that n1 pi d1 has to be equal to n2 pi d2. Okay, well, these things are just going to cancel, and what we're going to get is that n1 over n2 is just going to be equal to d2 divided by d1. And we can get this as a percentage. That percentage is what the speed will change by. Let's determine this fraction. So what is d2 going to be? Well, it's going to be 621.5, and then we're going to take away 8.5. 8.5 take away 1.6, which is equal to 6.9. And then we're going to divide this by the original diameter, which is equal to 621.5. And this here is just equal to 0.988 sort of reoccurring. Okay, so we can just take this and multiply this by the original speed of 70 miles an hour. So it's going to be 0.98, let's say 9, multiply this by 70. In my calculator, I've just kind of multiplied this as a fraction, which gives us around 69.2 meters per second. I think this is right. I think this is actually a really difficult question. Do let me know if there's a different way that you would actually approach it. Okay, question 13. An electric toaster illustrated in figure 10 draws a constant power of 1100 watts. When the toaster is turned on, the heating elements very quickly get up to their operating temperature of 300 C from room temperature of 20 degrees. Okay, so we're given some temperature gradients here in a time of 5 seconds. The elements made of nichrome with a specific heat capacity, etc. Quite a lot of info. We need to calculate the mass of the heating elements. So this here is a classic mixture between electricity and specific heat capacity. If you've not covered specific heat capacity at A-level, the formulas are identical compared to GCSE. We can just use that E is equal to mc times the change in temperature, typically given delta theta in A-level. Now, energy is power multiplied by time, which is equal to mc delta theta, meaning that, oh wait, we're looking for the mass, aren't we? So the mass is going to be power times time divided by c delta theta. Okay, so the power is 1100, time of 5 seconds. We're given the specific heat capacity, 450 joules per kilogram per Kelvin. The units are fine, multiplied by the change of temperature. So that's going to be 300 take away 20, which is 280. Let's see what we get. I swear I'm getting faster at using this calculator. This times 5 divided by 450 multiplied by 280. So it's going to be 0.044 grams. seems about right. Calculate the resistance of the heating elements. Okay, so we've got the power. We've got the voltage as well, so we could probably use P is equal to V squared over R. R is going to be V squared over P. What is V squared? 230 squared divided by the power 1100. This question seems a lot easier so far. So 230 squared over 1100. So that's around 48 ohms. Okay, the elements are made of wire with a circular cross-section diameter of 1 millimeter. Calculate the electrical resistivity of nichrome. Okay, well, R is equal to rho L divided by A, meaning that resistivity is going to be equal to RA divided by L. Okay, that's going to be equal to R times pi d over 2 squared divided by the length. Now, do we know the length? Okay, we don't know the length, but we're given the density. I guess this is why this question is a little bit trickier. I'm just going to calculate this over here. Because we're given the mass and we're given the density, we know that mass is density times volume, meaning that we can actually work out the volume, which is just going to be equal to mass over density. Okay, so what is that going to give me? 0.044 divided by 8.3. Oh, that was in grams, wasn't it? I've just spotted a little mistake over here. I'm not sure why I've left this in grams, but this here should be in kilograms, meaning that this here is actually 4.4 grams. So probably the easiest way is going to be to use this in kilograms, and then 8.31 grams per cubic centimeter. We can actually convert that to SI units. Divided by 8,310 kilograms per cubic meter. So this here is going to give me a volume of 0.044 over 8,310, 5.29 times 10 to the power of minus 6 cubic meters. Okay, so this here is the actual volume. Now, the length is going to be equal to the volume divided by the cross-sectional area. Now, since volume is equal to the area multiplied by the length, we can say, I'm going to take this for the length, which is going to be, what is it, volume divided by area. I'm going to plug this back all the way into here. Make sure that your work is organized for the exam, not like this. So this here will be equal to RA divided by, rather than the length, I'm going to write V, and then I'm going to get a factor of A squared. So what we're actually going to get is R pi squared D squared over 4, squared. Divide that by the volume. Let's plug in some numbers. So R was 48. Multiply this by pi squared diameter, which is 1 millimeter. 10 to the power of minus 3 squared is 10 to the minus 6 squared over 4. Divide that by the volume, which is 5.29. times by 10 to the power of minus 6. Okay, and this here will end up giving me around 5.597, let's just call it 5.6 times by 10 to the power of minus 6 ohm meters. Okay, part D. In reality, the power drawn by the toaster will not quite be constant. Explain what you would expect to happen to the power during those 5 seconds and why. Well, a couple of things that I noticed. We'll compare this with the mass scheme in a little bit, but number one, the resistance is likely to change. In fact, we can probably just say that the resistance will change. Because the resistance will change, the current will end up actually decreasing. We can be even more specific because with temperature, the resistance will, rather than change, we can write increase. And if the current will decrease, the power dissipated will end up decreasing as well. There's a little note that I've noticed in the mass scheme, and that is that the resistance of such alloys actually changes really slowly, so that the effect might be really negligible. But check out the official mass scheme for the official answer on this one. Question 14. Imagine that you're an ancient architect planning a pyramid. The pyramid illustrated is to have a square base of side 40 meters and be 40 meters tall. It's a solid made out of blocks of certain density. You want to calculate the energy required to build the pyramid. We're building a pyramid now. You know what the equation for the volume, calculate the mass of the pyramid. Okay, so first one doesn't seem really bad. So mass is density times volume. So it's going to be 2,500 multiplied by the volume, which is going to be a third, times the base area, which is going to be 40 times 40, and then its height is also going to be 40. Let's see what that gives us. 5.3 times 10 to the power of 7 kilograms. Next one, the blocks all need to be lifted to different heights, so to calculate the work required is tricky. An estimate can be made by modeling the pyramid as a set of 14 large cubes. 9 of them are placed together in a 3 by 3 arrangement. Okay, so you have basically something like this. The next 4 are placed on top of these to form a smaller scale. The next 4 are placed on top of these to form a smaller square. So we are going to have another 4 kind of here, and the last cube is placed at the very top. Okay, so that's probably going to be right in the middle, something like that. Okay, assume that the 14 cubes have the same total mass as the original pyramid. The bottom 9 cubes rest on the ground. Calculate the size and mass of each cube in this model. Well, at the top, so the height of the pyramid was 40 meters, wasn't it? And with this model, we just really have 3 layers of blocks. So the dimension, the size of one of these, let's say the height, which is all the dimensions because it's a cube, is just going to be 40 divided by 3, which is around 13.3 meters. Similarly for the mass, in the previous question, we found the total mass to be 5.3 times by 10 to the power of 7. So the mass of a single cube is going to be 5.3 times 10 to the power of 7 divided by 14, which is going to give me, let's call it 3.8 times 10 to the power of 1, 2, 3, 4, times 10 to the power of 6 kilograms. The final heights of their center of masses. Okay, so this question I think wants basically the height of the center here, the height of the center here, and the height of the center here. So the height of one of these is 13.3, and this one here is also 13.3. So the first one is going to be right there in the middle at a height of 13.3 divided by 2, which is around 6.65, which is about 6.7 meters. The other one is going to be, so let's say this one has a height 2. Height 2 is going to be 13.3 plus 6.7, which is going to be 20 meters. And then the next one is going to be at 13.3 times by 2 plus 6.7, whatever that gives us, which is height 3 is going to be 33.3 meters. Okay, next one, the total work done required to lift the high cubes into places. So the initial layer is not going to require any work done to be lifted, but the second and third layer will require. So the total work done just using mgh, or gravitational potential energy, is going to be equal to, let's just say, GPE. So it's going to be the mass of, how many of them were on the second layer? The next 4 cubes of place, so it's going to be 4 times the mass of an individual block, which is 3.86 times 10 to the power of 6. And then its center of mass needs to be lifted to 20 meters, plus the mass of the only cube at the top, which was 3.86, 10 to the power of 6. Oh, I've missed a factor of 9.8 here. So let me just add that in. Times by 9.81 plus 3.86 times 10 to the power of 6 multiplied by 9.81 and then multiplied by the height of the third layer, which is 33.3. And this here is going to give me 4.22 times 10 to the power of 9 joules. It's quite a lot of energy. Okay, C, if a very long wooden plank was leaned against one of the faces of the model from the ground horizontal to the top, what would the angle of the plank be with respect to the horizontal? Okay, so this here is basically a geometry question. So imagine you have something like this, then the total length of the side, let's call that L, then this here would have to be at the half point, which is L/2. Okay, well, if we consider the plank to be here, we could probably use some angles to work our magic. Well, this distance here is going to be L/2, this distance here will be L, and we want the angle to the horizontal, which is just going to be this angle over here. So we can say that, okay, this here is 90 degrees, so we're probably going to use the tangent of theta, tan of theta, where this angle here is theta, is going to be the opposite, which is L, divided by the adjacent, which is L/2. So these are going to cancel. 1/2 is just 2. Tan of theta is equal to 2. Theta is the inverse tangent of 2, which is around 63 degrees. Okay, if you wanted to build this model pyramid in a year, how many laborers would it take? Assume a manual laborer has a useful energy output of 800 kilocalories a day, where 1 kilocalorie is this many joules. So we require the total work done to be 4.22 times 10 to the power of 9 joules. Then we probably want to divide this by 365 multiplied by 800 times 4.18 times by 10 to the power of 3, like so. That's of course assuming that you work 365 days a year, which is definitely not going to be it. So 4.22 times by 10 to the power of 9. Divide that by 365 times by 800 times by 4.18 times 10 to the power of 3. We get around 3.45. So most of the marks are likely here going to be just for the calculation. So let's just say around 4 laborers. Okay, question 15. Two forces P and Q acting respectively horizontally and along the slope of a frictionless inclined plane can in turn individually be used to support a block of weight W on the slope. Two separate force diagrams sketch and label the forces that hold the block into place. Okay, so tell you what, let's draw the force along the slope first of all. So the force Q along the slope will have to support the weight, the component of the weight that's pushing it along the slope, which is going to be W sine theta. There's also going to be a normal component, W cos theta, which is supporting the vertical component. There are also going to be some vertical components. So here we have our diagram for the second case. We have the weight W is split into its vertical and horizontal components, and W sine theta, because this angle ends up being here, being theta right over here, is the horizontal component of the weight, and that's balancing out the force along the slope Q. W cos theta will be equal to the normal reaction. We can do the same if we had a horizontal force. So let's draw this. Now, I've extended this diagram actually into the question, but I just wanted to show that if that's the case, well, the horizontal force P has to be supported by the horizontal component of the normal reaction, because that's the only other force that has a normal reaction. So I've labeled this one N1, I've labeled the other one N2. Okay, so I think I've probably done a more intricate diagram that's necessary, because the next question is about resolving the forces in each diagram in suitable directions so you can obtain equations for P and also for Q in terms of W and theta. Okay, so obtain equations for P in terms of W and theta. The first one, which is probably easiest to write, is that Q has to be equal to W sine theta if this is supported, because this vector has to equal this vector. So the second part of the question is essentially done. For the first part of the question, we need to figure out P in terms of the weight. Well, we know that if this here is N1, then P has to be equal to, because this angle here will also be theta, N1, and then sine of theta, which is this component. Now we know that the other component, which is N1 cosine of theta, that's the vertical component, that has to be equal to mg, which is the weight. Let's just write that as W, like so. Therefore, N1 is going to be equal to W over cos theta. So this means that I can plug this into here and get that P will be N1, which is going to be W sine of theta over cos of theta. I think that's right. Part C, show how you could eliminate theta to obtain the following expression, and we're given something, take away something squared raised to a power of a half. Anytime we're looking for vector components, trust me, 90% of the time I'm going to have to use the fact that sine theta plus cos theta squared is equal to 1. Okay, just with that in mind, let's have a look at the previous equations. I might even just work a little bit more on this page. So I'm going to take equation 1 and I'm just going to rearrange that for sine theta. So we're going to get sine theta is, what is it? It's Q over W. And then we can probably get an equation for cos theta. Well, if we look back over here, you are going to spot that W sine theta is equal to Q. So we can also directly write that P is equal to Q over cos theta. and this would mean that cos theta is going to be Q over P. Okay, so we can just say that cos theta is, what is it? Q over P. Okay, so sine squared plus cos squared is equal to 1. This is going to eliminate the angle. So we can go Q squared over W squared plus Q squared over P squared is just equal to 1. Let's put these underneath a common denominator. So what are we going to get? We're going to get Q squared P squared over W squared P squared plus Q squared W squared over W squared P squared is equal to 1. We want to rearrange for W. So, right, Q squared, let's just carry on over here. P, that's a square, Q squared P squared plus Q squared W squared is equal to W squared P squared. Let's get all the factors with W on one side. So we're going to go Q squared, take away W squared P squared is equal to minus Q squared P squared. Let's flip these around. So W squared P squared take away Q squared W squared is equal to QP squared. Rearrange for W. Take a factor of W squared. What do we get? P squared minus Q squared is equal to Q. I keep forgetting the square. Q squared P squared. And I think we're basically in business. I'm going to fit this over here. So W should be plus minus the square root of Q squared P squared, which is just PQ over P squared take away Q squared, well, square rooted, which is raised to a power of half as required. Okay, this one here is really interesting. We've got a lion with eyes 80 centimeters above the ground, sees the sun set at 8 p.m. A giraffe stands with his eyes at 3 meters above the ground, and we've got the radius of the earth, and sketch a diagram with a side view of an arc. At the line of the horizon is seen from an eye located at the Earth's surface and an eye located at a small height h above it. Okay. And the line to the horizon is seen. This diagram is really connected with the next part of the question, so let's just draw this over here. Well, imagine that you have the radius of the Earth. Let's call this R, and we have some curvature. This angle here is going to be pretty small, and this diagram is definitely not going to be up to scale. So if we are right on the surface, as soon as the sun starts dipping below this line over here, we are going to get a sunset, I think. So if the sun is originally here, as it starts dipping and reaches sort of this point over here, it goes out of view. Now, if we are a little bit higher than that, and let's exaggerate it, let's say that this here is the height h. If we're lower, right over here, we'll not be able to see the sun, but we might have a direct line of sight with the sun if we're along here somewhere. Part 2 is asking us, hence obtain an expression for the approximate distance to the horizon D as seen by an eye at a height h. So before we tackle... My calculator fell again. Before we tackle these questions, I always tend to just write assume theta is small. Okay, so we know that the arc length S, which is this one here, is equal to r theta. Now, where will derive an expression for the angle subtended the center of the Earth by this distance. So this distance here is theta, and if you are at a height h, well, then your line of sight for the horizon is no longer r theta. Whereas if you're right on the horizon, if you're laying down and looking at the sunset on the beach, what your distance is r theta. But as soon as you jump up, that distance, that angular distance becomes smaller because the line of intersection is somewhere here. Now, where exactly is it? Well, this here is a difficult question. It's going to be smaller. It looks like it is about halfway. Update, the mark scheme does assume that it's about halfway. Exactly why that is the case, if you have any good ideas, please let us know into the comments. Really, really interesting question. So from similar triangles, we can say that this angle here is theta. So this distance here, s, is s over 2, and we can say that s is equal to r theta. And shall we just say that tan theta, which is approximately equal to theta, is going to be equal to h over s over 2, which is approximately going to be equal to h over r theta over 2, which is equal to 2h over r theta. Okay, now because theta is just equal to that, we can say that theta squared will be 2h over r, meaning that theta is the square root of 2h over r. Now I'm going to add an approximate sign because that has taken quite a lot of approximation. Okay, calculate the difference in angles corresponding to the different heights of the giraffe and the lion's eyes. Okay, so there's going to be two values. Theta is going to be 2 times 0.8. This here is for the lion. Divide that by r, which is the radius of the Earth, which is hopefully given in the question. 6370 times 10 to the power of 3. And this here is around 5.01 times 10 to the power of minus 4 radian. If we are using s equal to r theta, we're kind of automatically in radian mode. Now for the giraffe, theta will be equal to 2 times, what's the height of the giraffe? 3.5 meters, pretty tall. So 3.5 over 6370 times 10 to the power of 3. That's going to be 1.04 times 10 to the power of minus 3 radians. So delta theta is basically the angle for the giraffe, take away the angle for the lion. My calculator gives that as 5.47 times by 10 to the power of minus 4 radian. Okay, hence calculate the time at which the giraffe sees the sunset actually set. Okay, this here is a classic problem, and it's typically tackled with angular velocity. So, angular velocity is typically done in year 2, and you can think about this in terms of proportionality. You can define a quantity omega to be the change of angle divided by time, and that's just governed by the rate of rotation of the Earth. And 2 pi, which is one full complete rotation, or 360 degrees if we're working in degrees, is going to take 24 hours, so that's going to be 24 times 60 times by 60. So what we need to do is, if that's omega for the angular rate at which the Earth is rotating, we can figure out the time that it takes to cover a change of angle of this many radians, which is 5.47 times by 10 to the power of minus 4. So we can just directly rearrange for delta t, which is going to be equal to 5.47 times by 10 to the power of minus 4 multiplied by 24 times 60 times 60, that's 3,600. Divide this by 2 pi. I think that's right. Let's see what we get in seconds. Giving us around 7.5 seconds of extra sunset time for the giraffe to enjoy the sunset. I think I'm going to stop here for now. I'm going to let you guys have a go at the last question. Do let me know if you'd like me to do a separate video going through question 17 as well. What you definitely do now though is check out this video that we did last year with Lewis from Physics Online, in which we covered more questions from exactly the same competition that's going to give you the best chance of scoring the best possible mark. So click on this video right over here.